Over the last couple of lectures, we've learned about stars and the different properties that we can measure from these stars, like their temperature, luminosity, masses, radii, etc. And today we're going to talk about how a star is formed. And there's a lot of interesting physics that will go into that, and the places where these stars form in the universe we like to call the stellar nursery. So we can plot these features of a star on what we call an HR diagram, and for this diagram we're going to put the luminosity of the star on the y-axis and the temperature on the x-axis. And this diagonal strip that you can see through the middle of the graph is called the main sequence. And so stars on the main sequence are ones that are fusing hydrogen into helium in their cores. And today we're going to talk about how a cloud of gas in space can become one of these main sequence stars. And then in the next few lectures, we'll talk about what happens when a star leaves the main sequence and how it evolves to become a giant and supergiant and eventually maybe a white dwarf. So just to review how we read the HR diagram, which one of these choices is the star that has the lowest temperature? So I'll give you a few moments to think about this. So if we look at the graph, C is the option that's furthest to the right, and on this graph temperature decreases as you go to the right. So we want to pick the choice that's farthest to the right, and that's choice C. So it's interesting that even though C is the most luminous and has the largest radius, it's actually the coolest temperature star of these choices. So when we think about space as a vacuum, it turns out that that's not exactly correct. So for the most part, in between planets and sometimes in between stars, we can think about space as being empty or being a vacuum, but in reality there actually is a lot of gas and dust in between the stars, and we call this the interstellar medium. And so some regions of space have more gas and dust than others, and you can see this in the two images below. So on the left image, you have a region of space where if you look in the visible wavelength of light, there's this kind of black patch. So there's some gas in between, or in our field of view, that's blocking our view of those background stars. But if you look in the infrared, now the light from those stars is able to pass through that cloud of gas and dust, and we're able to see those background stars. But we can also see this kind of reddish glow, and that is the light being emitted by that interstellar gas and dust. So remember, if something has a low temperature, then it will emit light in the infrared. So this interstellar gas and dust is pretty low temperature, and so it is emitting most of its light in those infrared wavelengths. And it's in these clouds of interstellar gas and dust that stars will form. And so you can see an image here of a star forming region. There's this patch of there's a dark cloud of gas in the center, and there's these very bright patches where stars are either in the process of forming or have very recently formed. And so all this gas and dust in between the stars that makes up the material for the next generation of stars is called the interstellar medium. And so where you can see the dark patches, that's not because there aren't stars in that line of sight, it's because the stars in the background are being blocked out by this intervening cloud of dust. And then the very bright spots that you see are the new stars that have formed and have started to clear away the gas around them. So we've talked a little bit about where these gas clouds come from and how they can form stars when we talked about the formation of the solar system and the nebular theory. But to revisit that, you have this cycle where stars are born in these clouds of gas, and once they turn on their fusion reactions, they'll kind of blow any leftover gas out of their system, and then the star will go through its life cycle. But at the end of its life cycle, it's going to blow that material back into space and repopulate the interstellar medium with its gas. And then the next generation of stars are formed from the remnants of the previous generation of stars. And so you get this cycle where material from the previous generation is used in the new generation of stars. And when we talk about chemical abundances a bit later in the semester, that will be an important feature. So what kind of masses can we expect from these star-forming clouds? So a typical molecular cloud that you might find out in space will have a temperature of around 30 Kelvin, so that's only 30 above absolute zero, so they're fairly cold, but not exactly absolute zero. And they have about 300 particles per cubic centimeter. So that's not a very high density, but it's not a perfect vacuum either. And in order for one of these clouds to start collapsing, it needs to have on the order of a few hundred solar masses. And that's because even though this gas cloud has a very low temperature, it is still going to be emitting thermal radiation, and that creates a pressure. And in order for gravity to overcome that pressure, you need a significant amount of mass. And so remember, this is the eternal battle in the universe for a star, this inward pull of gravity and this outward pressure. And we're in a gas cloud now, so that outward pressure is not coming from nuclear reactions yet, but it's coming from just the fact that the gas itself has a temperature, and therefore it's going to be emitting some kind of thermal radiation, thermal pressure. So when the inward pull of gravity is able to overcome that outward thermal pressure, you can get your gas cloud out in space to start collapsing. And that's the first step to star formation. So here are some still images of a simulation of a gas cloud starting to form a star, and then we'll see a nice video version later. And so this is a ball of gas containing 50 solar masses, and it's about 1.2 light years across. And there will be some initial trigger that will cause the gas cloud to start collapsing, and in the next few lectures we'll talk about what that kind of trigger might be. So once the gas cloud starts to collapse, it's all not going to collapse into one single dense region, but you can get these lumpy regions, and so one gas cloud can actually lead to the formation of many different stars. And so some of those events that could trigger this collapse to begin, you could have a nearby supernova, so the shock wave emanating from that explosion could trigger your interstellar gas cloud to collapse, or you could have collisions between two different clouds. So these molecular clouds are orbiting in the galaxy, and so you might have two of these clouds hit each other, and that could trigger a gravitational collapse. Or, as we'll see a bit later in the semester, galaxies also move with respect to each other, and sometimes those galaxies will merge. And so if you have say, for example, two molecular clouds from different galaxies colliding, then you can trigger this formation, or even just a star from the other galaxy getting too close to your molecular cloud could cause it to start collapsing, and you get this beginning of star formation. And so now that we have our gas cloud collapsing, any region that is a little bit more dense than its neighbor is going to start collecting a bunch of mass towards itself. And so, like I said, you can have several overdense regions in a single cloud, and so you can make many stars from one single cloud. And so this is an example of a star-forming region in our galaxy. This is the Eagle Nebula, very famous image. So the one on the left is taken with the Hubble Space Telescope, and the image on the right is taken with the James Webb Space Telescope. And so these dark clouds are your interstellar medium, your stellar nursery, if you will, and the bright spots are where a star has formed and blown away basically the cocoon of gas that it formed in. And you can really see, if you compare the tips of the pillars in the visible to the infrared, you can really see a big difference. So in the tips and the visible, you can see some brightness, but then in the infrared, you can see the newly formed star really shining through the gas that's surrounding it. And that's because the size of the dust grains in these gas clouds block visible wavelength light more than they block infrared light. And another thing to note, especially with the visible wavelength image, these are what are called false color images. And so this is not necessarily what you would see with your naked eye, but these are images taken with different astronomical filters, and a color will be assigned to those astronomical filters on your telescope, and then you can create these pretty images. And that's also especially true for the infrared, because humans can't see infrared light, so we would never be able to see the image that we see on the right without introducing some visible wavelength colors to make this kind of image. And so here's a nice video of the process of star formation. So we saw the still images before, and now here it all is together in a video form.
All you need to make a star is hydrogen, gravity, and time.
Gravity pulls the dust and gas into a giant, swirling vortex.
Gravity brings matter together. And when you bring matter together and you squeeze things into smaller spaces, they necessarily heat up. It's a simple law of chemistry. You compress something, you drive the temperature up.
Over hundreds of thousands of years, the cloud gets thicker and forms a giant spinning disk bigger than our entire solar system. At its center, gravity crushes the gas into a super dense, super hot ball. Pressure builds until huge jets of gas burst out from the center.
That really shows you how violent a process star formation is. These jets are many light years across. Something is literally accelerating material very fast across unimaginable distances.
Gravity keeps the pressure on, sucking in gas and dust particles that smash into each other, generating more and more heat. Over the next 500,000 years, the young star gets smaller, brighter, and hotter. Temperatures at its core reach 15 million degrees. Only at that mind-boggling temperature can atoms of gas begin to fuse together, releasing massive amounts of energy. And just like that, a star is born.
Okay, so let's talk about the physics of how this star formation process goes. So we have our large cloud of gas, something triggers it to start to collapse, and then due to conservation of energy, as you're turning your gravitational potential energy of having all this mass spread over a large distance, you're going to turn that gravitational potential energy into thermal energy and kinetic energy. And so your gas cloud, as it becomes compact, it starts to heat up. And then as a consequence of conservation of angular momentum, as your gas cloud starts to collapse, it will start to spin faster. So that's the example of an ice skater spinning with their arms spread out and then pulling their arms in towards them and speeding up. So as the gas cloud heats up, that thermal energy will be radiated out into space. So as long as you have enough mass to overcome that outward thermal pressure, then you can keep collapsing and trying to form your star. But if you have too little mass, then that outward thermal pressure will be enough to halt your gravitational collapse. Now, conservation of angular momentum is causing our gas cloud to spin faster, but why does it collapse into a disk? So this is a consequence of regular momentum, not angular momentum. So as you have particles moving kind of randomly in this three-dimensional space, as they start to rotate, their overall momentum will be pointed in one direction. So even if you have one particle colliding basically with a momentum kind of pointing down and another with a momentum pointing up, when they hit each other, their average momentum in the up-down direction would cancel out, and all that's left is the momentum in the circular direction caused by conservation of angular momentum. So the conservation of linear momentum is what causes the flattening of your gas cloud into a disk. Another consequence of conservation of angular momentum are the production of these protostellar jets. So now you have a protostar in the center of your gas cloud, so it's a very dense, very hot object, but it has not yet started doing nuclear reactions in its core. And so material is being drawn towards the star, but not all of that material can be taken in by the star. So as a consequence of angular momentum, some material that gets really close to the star and it is close to being absorbed by the star is instead being ejected in these huge jets that are coming off of the poles of the star. And when this jet of material hits the interstellar medium, it produces light. So these jets themselves are not light that's being emitted from the star. These are gases, material that were close to falling into the star, but instead were ejected out of the system. And when they bump into other gas particles in the interstellar medium, they light up and we can see that light. And these protostellar jets can be very, very big. So the previous picture, the jet pictured there, was about a quarter of a light year, and here this jet is about 1,000 AU. And remember, an AU is the distance between the Earth, the average distance between the Earth and the Sun. So this is 1,000 times that distance. So these jets are very large, and so these protostars are actually ejecting material very far out of their system as they're forming. So that might raise the question then, why do these protostars have jets but the Sun does not have a jet? And I'll give you a minute to think about why that may be. Okay, so the Sun is no longer a protostar, it's a full-blown star, and so when it starts doing fusion reactions, a star will generate a solar wind that will blow any remaining gas and dust out of the system. So there's no leftover material to spiral in towards the Sun to generate these large jets. So it can take a while, even as a star is doing fusion reactions, to go from a protostar to being on the main sequence. And the time for that transition to happen will change depending on the mass of the star. So for very low mass stars, that transition can take tens to millions of years, and then for higher mass stars, that can take tens to hundreds of thousands of years. So for something like the Sun, it might take 30 million years to go from a protostar to becoming a main sequence star. So to summarize everything, you have this large gas cloud out in space. Something will trigger a collapse, and then gravity will cause the gas cloud to start to shrink. And if there's enough mass and different regions with different densities, then it can fragment and you can get several different stars forming from the same gas cloud. Then as the cloud gets smaller, it's going to heat up in the center, and eventually the center will get hot enough that you get fusion reactions, and then those fusion reactions will produce enough energy to stop the gravitational collapse, and you have a new star that is relatively stable that will last for varying amounts of time depending on the initial mass of the star. And when we were talking about the HR diagram, we said that the mass of a star really determines all of its important properties. And so we're going to talk about what different masses we can expect from stars forming in these gas clouds. We think that the Sun must have formed in one of these gas clouds with other nearby stars, but has since migrated away from its brothers and sisters. So when we look at stars in space, we see that there are many more low mass stars than there are high mass stars. So the low mass stars are very common and the high mass stars are very rare. And so there are limits that we can place on the high mass side and on the low mass side. For the high mass side, if you have a lot of mass, then you're going to have a lot of gravitational potential energy in your gas cloud, and converting all of that gravitational kinetic energy or gravitational potential energy into thermal energy can lead to basically too much outward pressure for your mass to overcome. And so when we do models of this behavior, we see that there is an upper limit to how big your gas cloud is before the radiation pressure that happens in the lead up to star formation, there's a limit to how much that can be. So when we do observations in space, we haven't found any stars that have more than 300 solar masses. So somewhere in this range, you generate too much radiation pressure and you can't collapse completely into becoming a star. On the lower mass side of things, there's not this overwhelming radiation pressure that can stop you from contracting, but it turns out that there is another form of pressure that will halt the collapse of a gas cloud into a star. And we need to keep collapsing to increase our core temperature to 10 to the 7 Kelvin in order to start our nuclear reactions. And this lower mass limit turns out to be about, or exactly, 0.8 solar masses. So on the upper end, we have about 100 to 300 solar masses, and on the lower end, we have 0.08 solar masses. So I'll give you maybe a minute or two to think to yourself, what kind of pressure is there other than the radiation pressure that could stop the collapse of this gas cloud? And the hint that I'll give you is it might be something that you've seen in another science class, like maybe a chemistry class or an upper level physics class if you've taken any of those. Okay. So it turns out from quantum mechanics, and maybe you've seen it in chemistry, there is something called a degeneracy pressure. So when we're talking about atoms in a gas cloud, we're going to assume that the atoms are neutrally charged, so they have the same amount of protons and electrons. And when you try to push different atoms close together, the electrons will, of course, repel each other electromagnetically, but you can overcome that electromagnetic force, but there's an additional force due to the electrons that will prevent you from compressing that matter any further. And so this is called degeneracy pressure. So from quantum mechanics, there are rules that say where electrons are allowed to orbit a nucleus. And so there's these different quantum numbers, one dealing with the orbital level, and then a couple others dealing with, say, the shape of the orbital, the orientation, and its spin. And quantum mechanics says that you're not allowed to have two electrons that have all four of the same quantum numbers. So what happens in these gas clouds is they get to a point where the inward pull of gravity is not great enough to overcome this degeneracy pressure. And that's a consequence of not having enough mass. So the really large gas clouds have enough mass to overcome this degeneracy pressure, but the smaller mass gas clouds do not. And so here's some analogies comparing thermal pressure and degeneracy pressure. So for thermal pressure, you have a balloon filled with a set number of air molecules, and when you heat those air molecules up, they'll start to move faster and push against the edges of the balloon, making it expand. So that's the kind of pressure that you can get from heat. And for degeneracy pressure, if you imagine playing musical chairs and the room has more than enough chairs for everyone present, then it's very easy to find a place to sit. But if we take away a bunch of chairs, for example, implementing our quantum mechanics rules, now there might not be enough places for people to sit, and so there's going to be some pressure preventing the gas from occupying the smaller area or smaller volume that the chairs are occupying. And so this, we call it a pressure because it's in opposition to the inward pull of gravity. And so there are objects that were forming in a gas cloud that just didn't have enough mass to overcome this degeneracy pressure, and therefore this object was not able to get hot enough to do fusion reactions and become a star. And that very specific 0.08 solar masses is the mass that you need to overcome the degeneracy pressure to start doing hydrogen fusion reactions. And so these objects that form in these gas clouds that just don't have enough mass to become a star are called brown dwarfs. So these are objects made out of gas that do not do hydrogen fusion in their cores. If you remember, we said that low mass stars were more common than high mass stars, and so if you continue that down for masses even lower than the mass of a star, then we should have a lot of brown dwarfs. The problem for astronomy is if we're trying to detect things using light emitted from those objects, then brown dwarfs are going to be very hard to find because they do not do fusion reactions and therefore they don't emit a lot of light. These brown dwarfs are a little warm though, so they do produce quite a bit of heat, just not quite enough to do nuclear reactions. And so we can find these brown dwarfs by looking into the sky in infrared wavelengths. So the image on the left, all of the circles are actually where brown dwarfs are. And so they have heat left over from the formation process, and some of them even do a special type of fusion reaction involving deuterium, which is an isotope of hydrogen. But they're not doing the typical proton-proton chain in their cores, and so we do not consider them to be stars. Eventually, these brown dwarfs will fade because they don't have the continuous energy output of the nuclear reactions, and the infrared wavelengths are really the best way that we can look for these objects. And if we add the brown dwarfs to the HR diagram, then we get something like this. So on the lower side of things, a brown dwarf needs to be about 13 times the mass of Jupiter in order for it to be a brown dwarf, and the upper limit is the 0.08 times the mass of the Sun, because if it's any more massive than that, then it would trigger nuclear reactions and become a star. So a lot of people will say Jupiter was very close to becoming a second star in the solar system, but that is not true at all. So Jupiter is an order of magnitude too small to be even a brown dwarf, so it's nowhere near enough mass to become another star. And we can find these brown dwarfs orbiting other stars. So remember, binary systems are very common in our galaxy, and so it wouldn't be surprising to find a brown dwarf orbiting a star. And we can also find brown dwarfs that would have been the center of their own solar system had they had enough mass to turn into a star. And in fact, the third closest system to the Earth is a pair of binary brown dwarfs called Lumen 16. So, what is the physics term that stops a brown dwarf from collapsing into a star? Okay, so it's electron degeneracy pressure. When we start talking about more exotic things like white dwarfs and neutron stars and black holes, we'll talk about what kind of other degeneracy pressures and what other kind of forces are present when we start talking about very dense forms of matter. So to review, stars are born in these dense molecular clouds in the interstellar medium. Something causes that gas cloud to start collapsing, and then if it has enough mass, the center, very dense, hot region of that gas cloud will become a protostar, and the protostar will fire jets out into space, and then once it starts doing nuclear reactions in its core, it will become a star. And if you have too much mass in your gas cloud, then the radiation pressure might blow your cloud apart before it has a chance to start doing nuclear reactions in the core. And if your gas cloud doesn't have enough mass, then there won't be enough gravitational potential energy to overcome the degeneracy pressure, and you will end up with a failed star or a brown dwarf.